Our text starts out talking about the Michelson-Morley experiment as the most famous experiment designed to detect the small changes in the speed of light. But I feel like rushing to the most famous experiment kind of skips over a lot of the other experiments that were related experiment and the related hypotheses. First of all, let's talk about for a second, what is it that the Michelson-Morley experiment was actually trying to determine? And what it was trying to detect was this idea, the luminiferous ether. The dominant explanation for the physics related to the speed of light before the Michelson-Morley experiment was that light travels through a luminiferous ether, much like sound travels through air. This luminiferous ether should have its own velocity, and it should in principle be possible to determine our velocity with respect to such an ether. Also, our velocity with respect to this ether must be changing as we go around the sun. Now, one of the reasons that the Michelson-Morley experiment became so famous is that once the Michelson-Morley experiment failed to obtain any evidence that the velocity of Earth can be measured against the speed of a luminiferous ether, physicists and philosophers divided into camps. Some believed the reason that the speed with respect to the ether could not be measured was because Earth fully dragged the ether along with it. So let me kind of try to put it this way. The Michelson-Morley experiment was actually compatible with special relativity, but it was also compatible with the concept of full ether drag, while stellar aberration is compatible with special relativity, but is incompatible with full ether drag. And also I should put in luminiferous ether, the idea that light is like sound, and like the sound waves are carried in air and light waves are carried in luminiferous ether. For that, Michelson-Morley proved incompatible, while stellar aberration was compatible. So the only ones of these three propositions, special relativity, full ether drag, and luminiferous ether, the only one of those explanations that actually works is special relativity. Now let's take a second to talk about the more broad history of the experiments related to the speed of light. In 1676, Ole Romer made careful measurements of the orbital periods of Jupiter's moons as Jupiter moved away and toward the Earth, and from those careful measurements he was able to obtain one of the first, possibly the first, estimate for the speed of light. But then in 1729, about 40 years later, James Bradley was making careful measurements of the directions to stars in order to find a phenomenon called parallax. The idea of parallax is actually something you instinctually apply when you have both of your eyes open. The two images coming into your eyes are slightly different, and the more different the two images are, the closer the objects appear to you. You also have this experience when you put on a pair of 3D glasses to go in to a movie theater and to watch a 3D movie. Basically makes it so the images seen by the two eyes are a little bit different, and it makes it so you see depth in the image. So anyway, Bradley was looking for parallax by looking at the stars at times separated by several months, thinking to widen the eyes of his telescope. However, he discovered an unexpected phenomenon while he was doing this. What happened was that as the Earth moved around the sun, the stars would actually shift forward and backward towards and away the direction that the Earth traveled. An exaggerated description of stellar aberration is kind of shown here, and I'm not sure, I mean, this isn't 100% mathematically correct necessarily, but I just wanted to try to give an idea of what James Bradley was seeing in the stars. Here's an animation from Wikipedia that kind of shows the effect of stellar aberration. Now, if you are looking through this telescope, then you see the star at not at directly vertically above you, but you see the star at an angle. This star here, the source of the image, starts from here and basically goes, well, it's going straight down, but anyway, this is pretty much, neither of these views are special relativity. Actually, I would say that the one on the left is probably luminiferous ether, and the one on the right is full ether dragging. Luminiferous ether on the left, full ether dragging on the right. And what we want to do is see what does special relativity say. So actually, I made this demo myself. Okay, first of all, we're going to examine what it looks like. I've basically combined that telescope that has, so that the idea of stellar aberration can be shown, with the concept of Michelson-Morley experiment. So the star is up here, it emits a flash of light, the flash comes through this window here, and then it reflects off through this two-way mirror, so that some of the beam transmits to the left, some to the right, or some to the right, some down, and then everything rejoins when it gets back to the reflection point. Now what I'm going to do is change the relative velocity between the star and the emission event, and basically I'm going to cause the this apparatus, the blue box, to move, and this is what happens under the Lorentz transformations of that. This is what things look like in the star's frame of reference. In the star's frame of reference, the light enters the left-hand side of the telescope before it enters the right-hand side of the telescope, and that difference in timing means that the light is also going in a different direction. But ultimately what happens over here to the left side and to the right side is that you get the same interference pattern, but this is the what do you call it, the special relativity version of what is going on. So again, this is basically luminiferous ether. This is full ether dragging. And this is special relativity. Now, the Michelson-Morley experiment was compatible with the idea of full ether dragging, but incompatible with the idea of luminiferous ether. Stellar aberration was incompatible with full ether dragging, but compatible with luminiferous ether. But special relativity is compatible with both. Okay, I'm going to fill in this table with a couple of more things. First, the Fizzo-Foucault, what I call the air experiment, to distinguish it between the Fizzo water experiment. The Fizzo air experiment, they built this 720 cogwheel, and sunlight was sent through the 720 gaps in the cogwheel to a mirror that was 8 kilometers away, and then reflected back through the same cogwheel through a different gap in the same cogwheel to a detector. The cogwheel could be spun up to hundreds of revolutions per minute. So a quick calculation, the minimum speed of rotation for this thing to work at is traveling from to the mirror and back again. That is 16,000 meters. It's going to do that at a speed of 3 times 10 to the 8th meters per second, the speed of light. And it's spinning, it has 720 cogs per revolution. So I can multiply this and take the reciprocal, and I get 26.1 revolutions per second. So that's very fast. But it was engineered so that it could actually rotate 7 times that fast. So anyway, I say that this this experiment was more or less compatible with special relativity, whether or with full ether drag or with a luminiferous ether. It measured the speed of light, but it didn't make any particular claims about the nature of geometry. It just measured the speed of light with respect to that cogwheel and that mirror. Now the final column and the final row here is about partial dragging and the Fizzo water experiment. The reason I put it here is because you get into conversations with people and they talk about, and I think I'll be honest, I'm guilty of it, because I had no idea what partial dragging was when I first got into it, and so I have brought up partial dragging in conversations where I didn't realize that it was completely irrelevant to the topic. The issue with partial dragging is that it's part of an experiment that I'll call here the Fizzo water experiment. Now, in this experiment, basically, you're measuring the speed of light as it goes through this water, and this water has a velocity coming one direction, and then you can double up by going back through water coming in the other direction. So in both directions, you have the light going in the opposite direction as the water or in the same direction as the water, depending on how you set it up. The reason that this is kind of irrelevant to the question of luminiferous ether is because the question about luminiferous ether is whether some luminiferous ether occurs in a vacuum. But the question of this Fizzo's water experiment is whether the water exists, whether the water in this experiment exists. And you absolutely know for a fact that the water in this experiment exists. And so you are quite right to consider whether the speed of light is dragged with that water or not dragged with that water. And you find that, yes, the speed of light is dragged with that water. So the conjecture would be, if we've got the velocity of the water, is the velocity of the light through the water equal to the velocity of light plus the velocity of water? That would be full water dragging. Now, the relativistic version of how fast the velocity of, not the velocity of the water, but the velocity of the light in the water is, well, first of all, let's fix this, because we don't want the velocity of light to be the velocity of light in the water. The velocity of light in the water is v light over n, the index of refraction of the water. And then you can calculate relativistically what the speed of the light in the water is with what's called the relativistic velocity equation, which I'll get into more later. And here I'm saying that the partial dragging theory is compatible with the Fizzo water experiment, and the special relativity version is compatible with the Fizzo water experiment. But it's not because they're the same, it's because they're very, very close. Now, when mathematicians talk about things being very, very close to each other, a lot of the times what they actually mean is that the two functions are approximately the same over a very limited region. Right here, the black dot represents the expression for the full drag, where you're just adding the two velocities. The blue dot represents the relativistic expression, which is valid over the domain where the velocity of water is between the speed of light and the speed of light, between negative speed of light and positive speed of light. Those are okay parameters. The Fresnel drag is a linear expression, which is very, very close to the relativistic expression, especially if you zoom in to around here And if you get far enough in here, you can't tell any difference between those two lines. And in fact, pretty much any experiment that you're going to be doing with water, with a flow of water, is going to be very close to this region, because you're not going to have the flow of water be anywhere near the actual speed of light. So since every experiment that Fizzo did with his water experiment had the water flowing at a velocity between, say, here and here, there was absolutely no difference between the relativistic expression and his linear expression for it. But if you go back and look at the full domain of possible water velocities from negative speed of light to the positive speed of light, there are large differences between the expression Fresnel's partial drag equation and the relativistic drag equation. But either way, the Fizzo water experiment is rather irrelevant to the question of full ether drag or luminiferous ether, because in the Fizzo water experiment there was water, and the light was dragged with the water. Okay, let me just kind of go through this diagram a little bit more, try to specify. Notice on the x-axis it's labeled medium velocity. So if the medium velocity is -1, then the speed of light through that substance will also be -1, according to the relativistic expression. If the medium velocity is +1, then the speed of light through it will also be +1. So then we have everything in between. The speed of light, and this is kind of strange because you have this speed of light going through something of the opposite direction, and you actually get negative velocities out of it. This is weird. I mean, you aim your beam through something coming toward you. You aim your beam of light towards something coming toward you, and it actually comes back at you while it's going through that substance. So that's kind of an amazing thing. Fresnel's drag doesn't necessarily have that effect, but let's look at what happens when we make the index of refraction 1, which is what the index of refraction of a vacuum would be. Now look what happens. Now the speed of light for Fresnel and the speed of light for the relativistic are exactly the same, and no matter what the speed of the medium, the speed of light is equal to the speed of light of, no matter what the medium velocity is, the speed of light is going to be +1. So we aim the light through a medium with index of refraction 1, and it remains at the speed of light. Let's think for a second about air. Air has a medium of refraction of 1.000293. I'm going to plug that into my demo and see what happens. All right, there it is, 1.00293. Now, what it looks like is we still have this difference between Fresnel's partial drag and the relativistic. If you have air coming at you at 99% of the speed of light, then it will actually, and you send a beam of light through it, the speed of light, the light through it will be actually slowed down a little bit. But I don't know how far we have to zoom in, but I'm going to zoom in here and see, okay, 0.95, 0.98, 0.99, 0.995. So if you had that light if you had that air coming toward you at looks like 99.7% of the speed of light, you sent a beam through that light then basically that light would come to a complete halt inside that oncoming air. So I'm saying that partial dragging is irrelevant to the question of the existence of a luminiferous ether, because the assumed properties of the index of refraction and the velocity in the formula for partial drag belong to a known physical medium, such as flowing water, rather than to an unknown medium that's usually described as luminiferous ether. As not to say the question of partial dragging should be entirely discounted, though, as there may be interstellar gas throughout the universe which might be described as having an index of refraction and velocity over large regions of space.